now we're ready to expand. So we've done all the legwork. Well, a good amount of legwork. We'll have to do more, but we're ready to expand. So we expand our amplitude of the Ginzburg-Lambda equation, which depends on x and t, and we wrote those as if they were fast variables because we introduced super slow variables. So that's an a naught, the amplitude is order 1 in general, times, not times, as a function of phi, which depends on x and t, and a slow time and a slow space, plus higher order terms, phi x t plus and so on. And in principle, we actually, this thing here, we introduced this capital phase as 1 over epsilon times capital phase, which depends only on the slow variables. So that, okay. So the A depends now on 3 variables, the phase, which is essentially the fast space, but written as a capital phase, which depends slowly on space. So that's a technical thing, but conceptually it's the fast space. It's where it's periodic. A is periodic in this argument. We'll see that, but just anticipating. And then the slow variables. So we need to rewrite now our Ginzburg-Lambda equation in terms of those variables. So what happens? So we have the derivative with respect to time. That becomes, time shows up both in the phase and explicitly. So this is going to be d by d phi. I'm going to use the little phi because that's denoting the first argument of the amplitude. Okay, d by d phi times epsilon squared d phi by dt. But we're writing this in terms of a capital phase, and so we have epsilon d capital phi dt times d by d phi. Okay. Well, of course, there's also the explicit time dependence here, which is order epsilon squared. So it turns out we don't need order epsilon squared eventually. So I'm just going to write down here plus order epsilon squared. And that should have been here also, but fine. Then the same thing happens in terms of space. So the derivative with respect to the space becomes a derivative with respect to the phase, and then the phase with respect to slow x plus epsilon times d by dx. But we remember again this this phase, if it's a capital phi, then it cancels the epsilon, and capital phi with respect to capital X is q. So this is simply q times d by d phi plus epsilon times d by dx. Okay. So now we need to have the second derivative. So that's a little extra work, and we have to be careful. So let me write it out, because it's actually q times, a q is a function of slow variables, right? So we need to keep that in mind. And so we have this thing times, again, q time of d with d by d phi plus epsilon d by d slow x. And the reason I wrote this out like that is because one has to be careful. This slow derivative acts not only on a, you have to imagine now that there's of course an a sitting here, so I just wrote it as operators. So this derivative acts not only on this a here, but by product rule also on this q. But that's not true for this slow derivative. That slow derivative only acts there. So that has to be, one just has to pay attention to that. Okay, so now we multiply this out, so we get q squared with the second derivative and so on. So we get q squared, second derivative with respect to the fast phase, plus 2 times this mixed product, this and this. And in that factor 2, the slow derivative does not act on q. So this is actually going to be q times d by d slow x d by dq. And then comes this term where this acts on here. So we get plus epsilon dq by d slow x times d by d phi. And then comes finally plus epsilon squared, second derivative with respect to slow x. Okay, that's fine. So now we can plug in. Okay, maybe I should simply quickly write down our Ginzburg-Lambda equation again so we know what we actually have. So we have d by dt of a is equal to the second derivative of a with respect to x plus mu a minus a absolute value squared a. And so we expand a in a naught and a1 in higher order terms and put all these derivatives in. Okay, so let's look at the leading order. Since a is order 1, we actually have a leading order term which is order 1. And the time derivative has an epsilon, so there's nothing on the left hand side, but the space derivative has an order 1 term. Okay, so we have therefore 0 is equal to q squared dA0 by d phi squared plus mu a0 minus a0 absolute value squared a0. Okay, that's familiar. That just gives the fixed point around which we are expanding. And so we have that basic solution a naught is equal to the square root of mu minus q squared. And let me actually make explicit that q depends on space and time. And this is e to the I phi. Okay, so we have now that a naught depends on phi, the phase phi. That's this periodic dependence I mentioned. But it also depends on the slow variables x and t through the wave number. So that's why we made that ansatz like that. Right? Okay, good. Next order. Order epsilon. So now we have on the left hand side from the time derivative, we have d by d phi by dt. Okay, let's put that down. So we now have d capital phi by d slow time dA naught by d phi. We don't have an a1 term because the time derivative has no order 1 contribution. So that's everything that's on the left hand side. Okay, so now maybe we should first go for the terms that involve a1. So that means we only take the terms that are order 1 on the right in terms of the derivatives. So we actually only have this term with the a1. Okay, so we have d2a1 by d phi squared times q squared plus mu times a1, and then the linearization of this guy around a naught. And so this is actually an a naught squared times a star. So we have 2 a naught star times a1, and then also minus a naught squared a1 star. Okay, so that's everything that involves a1. And so now the stuff with a naught, which comes from the derivative at order epsilon. So that's these two terms. So let's put that down. So we put plus 2q second derivative with respect to slow and with respect to q of a0 plus dq by dx d by d phi a0 and that's it. So So now the question is, what structure does that equation have? So it's an order epsilon equation, so we think we should be able to solve for A1, right? So let's write it as an equation for A1, which has certain inhomogeneous terms. And let's see what we get. So we get, I put that stuff on the left-hand side, so I get q squared d by d phi squared plus mu minus 2a naught absolute value squared minus a naught squared. And I want to write this as acting on A1, right? So I have an A1 here, an A1 here, an A1 here. So that's okay. Here I have an A1 star. So I have to do something here. So let me introduce a notation that's just, we're going to use that just right here and never else again. I put like a curly C here for a complex conjugation. So therefore this term generates this term. And we see that this is a linear operator. Let's call it L. And it, on the right-hand side, we have an inhomogeneous term, which is minus d capital phi by dt, dA naught by d phi, plus 2q second derivative of A naught with respect to x and q, and derivative of q with respect to x times dA naught by d phi. Okay, so that's the equation we get at order epsilon. And the question is what to do. Probably you already expect that there's something going to happen, because actually when you think of it, the structure is very similar to what we did in all the other problems, except you know, different slow variables and all that kind of stuff. But at order 1, we would have thought we would determine what we want, which is essentially we want to have an equation for q of x of t, right? That's, we want to have an evolution for the wave number, or the phase, either way. And we don't get that. We got an equation for A naught, which depends on that q of x and t, but the q of x and t at this point is completely arbitrary. So we go to next order, and there we want to determine A1, and therefore to do that we need to invert L, and as always the question arises, is L singular or not? Okay, so we need to figure that out. Now the basic assumption, or the fundamental assumption I should say, for this whole analysis is that the system is translation invariant. So it's infinitely long and is translation invariant. That means that in our original Ginzburg-Landau equation, the coefficients don't depend on x. Don't depend on t either, but that's okay. They don't depend on x and t, but let's focus on the space dependence. So that means, as we saw in this last time when we looked at the Swift-Hornburg model, we saw that this implies that the linearization around that periodic solution actually has a zero eigenvalue, and the eigenvector was the derivative. We saw that in the Swift-Hornburg model, and so since that seemed to be really a general feature, it should be the case here too. And so let's see. The coefficients are indeed independent of space, right? And if we go to our equation now, this equation doesn't have any x in it, but x has been replaced by the phase, right? We just rescaled the spatial coordinate with a local wave number. And so the phase plays now the role of space, and indeed this equation here at order 1, this equation does not depend explicitly on the phase. So the spatial translation invariance is simply the fact that these coefficients don't depend on the phase. And so therefore again, we can take the derivative of this thing with respect to the phase, which is motivated by that if we shift the solution a little bit over, it's again a solution, and so it shouldn't depend on that shift, and the derivative with respect to that arbitrary shift is the same as the derivative with respect to the spatial variable. Anyway, so we take the derivative of that and see what we get. Okay, off we go. Take a derivative with respect to the phase. So we have, unfortunately, there's not enough space to have both on the screen, so let's think about it beforehand. When I take a derivative with respect to the phase, I simply get the third derivative, which, and here I get the first derivative. So with that in mind, I'm going to think of this third derivative as the second derivative of the first derivative. Okay, and then I have mu times the first derivative, so both of these terms are just have the first derivative. And similarly here, when you take a derivative here with respect to the phase, you get a derivative of a naught with respect to the phase. And also there's the a star here, right? And we get also derivative of that with respect to the phase. So that's what we get. And so let's write that out. We get then simply d by d phi of equation above. We get q squared d second derivative of dA by d phi. Right, that's what I said. The third derivative becomes the second derivative for the first derivative, plus mu times the first derivative, and then come the nonlinear terms minus 2 times a naught absolute value squared minus a naught squared times, right, if we look here, this is the a naught squared, and then there's an a naught star, and we need to take its derivative, so that's what this is. I put here again my complex conjugate operator, and so this is that term. So I guess maybe you saw that instantly, and I didn't have to say that much, but this is of course also L. And this whole equation here is 0, right? So this is 0. And so we see that, as the general argument suggests, that the derivative of the solution that we're looking at and that we are expanding around, that derivative is a 0 eigenvector. It's an eigenvector with eigenvalue 0 with lambda equals 0, and it's that translation mode. Okay, so L is singular, and that means we get a solvability condition imposing stuff on this inhomogeneity on the right hand side, which is good, because that's where you see we have a time derivative of the phase, we have some derivative of q is the derivative of the phase, and we have some other terms with the phase. So this will give an evolution equation for the phase if we only figure out how to do the solvability condition. So we now need either the eigenvector for the adjoint, or we need to have the left eigenvector of L, either way. Now, when you talk about the adjoint, of course, you need a scalar product. And so we need to define a scalar product, because we're living here on the PDE, right? This is not a good old matrix. This is a PDE, oh, an ODE. Okay, it's an ODE, differential equation. So we need to be explicit about the scalar product we want to pick. And it turns out that in this case, one has to be careful, or not, and doesn't have to be, but if you're careful with the choice of that scalar product, you can save a lot of work. Let's just put it that way. But before I do that, actually, let me make a couple of more general comments that are really important. I said that this is singular and has this eigenvector. And what we need, let's be precise in under what condition that actually happens. I mentioned that the system is translational invariant, right? Okay, that we have to have this symmetry of the system, so the coefficients are independent of space, translation symmetry. But we need more, because if A naught did not depend on the phase, then this would be 0, and it would not be an eigenvector at all. You would still have this equation, but dA by d phi is 0, and so it's not an eigenvector of L. And L wouldn't be singular. And so what you need is that you have this translation symmetry, but you're expanding around a solution that breaks that same translation symmetry, right? Because we have a solution that's periodic, so it's not constant, right? We have this solution and it breaks the translation symmetry in X. And so that's why this kind of slow dynamics arises from the presence of a continuous symmetry, which is broken by the solution that we're looking at. And we have a continuum of solutions along in that, if we apply that symmetry, so to speak. Okay, good. So now we need to worry about that scalar product. So usually we have a complex function, and right. The other thing we note is that A naught is periodic, right? So we're looking at periodic functions A naught. So we're actually living on the space of periodic functions. And so we would usually put a scalar product down like the following. We would say we have, if we have two functions, let's call them psi1 and psi2, just some complex functions, then usually we would integrate over the space, and it's 2 pi periodic, so we just integrate from 0 to 2 pi, and these are complex guys, so I would have psi1 star times psi2 d phi. That would be our scalar product. So why is this an issue, or why is that a question? We need the left eigenvector of L, or we need the eigenvector of the adjoint, either way. And so if L was self-adjoint, then the fact that we have a right eigenvector would give us instantly the left eigenvector. Or, since if L is self-adjoint, the eigenvector would also be the eigenvector of the self-adjoint L. But if L is not self-adjoint, then we would have to solve a new differential equation, which of course we'd rather not do if we can help it. And so we need to check whether with that scalar product the L is self-adjoint or not. And so self-adjoint would mean that if I apply L, not this L, curly L to the right guy, it would have to be the same as if I apply it to the left guy. If self-adjoint. That's the definition of self-adjoint. Okay, so we need to calculate them. We need to calculate both sides and see whether they're the same. Okay, off we go. We have psi1 times L psi2. And this would have to be true for arbitrary size, right? It's just a general scalar product. So that will be the integral from 0 to 2 pi. I'm not going to write the limits further. And so this would be psi1 star times L acting on psi2 d phi. And where's our operator? It's sitting up here, so we need to squeeze that in here. So that's the integral of psi1 star times q squared d by d phi squared plus mu minus 2a naught squared minus a naught squared complex conjugate of psi2. That's what this is. And this object here, that's a naught squared. No, I can't do it that way. Sorry, I'm jumping the gun. So what do we need to do now? We need to compare that with the right-hand side here. And that means we want to have the operator L acting on psi1, which is sitting here. So the standard thing is for the derivatives, you take integration by parts and roll it over. Because the function is periodic, the boundary terms don't contribute, so you can simply roll this over twice, and so the minus sign disappears. So this term here is self-adjoint. We can simply roll it over. Maybe I should start writing it so we don't have to say so much. So I have here therefore a q squared d2 d phi squared of psi1 star. Then I have a mu psi1 star, because that's just a scalar, right? We can put that here, we can put it here. And then I have the 2 a naught absolute value squared, which is also a scalar, so that's fine. That's times psi2. This is good. And then I have to write the other term. I'm going to write this other term, which is minus psi1 star a naught squared psi2 star d phi. Okay, so let's see, what do we have? Let's compare this guy with this guy. So if we apply, maybe we don't have to write it out. If we apply L to psi1 in the left slot, then the L is, the second derivative, but these numbers are real, so the star in the left slot makes no difference, but it's applied to psi1 star because the first argument of the scalar product is star, so we have this. Then the mu is psi1 star, and this is psi1 star, that's exactly this object, multiplying with psi2. So this term matches that term perfectly. How about this one? This one here would be, maybe, let me write it out after all, at least this last guy. So if I had L psi1, psi2, I would have, let me sort of denote this as a square bracket. I would have this guy, and then I have still to do this last term. And so if I do L of psi1, I have the integral, and L is now an a naught squared is L, but it's in the left slot. That's the from the L, and I need to put a C there. It's in the left slot, so therefore actually it has to be a star. So this is a naught star squared. And then I have, what else do I have? L is acting on psi1, so I have a psi1 star. This C is premature. So L on psi1 is L multiplies with a naught squared and then takes the complex conjugate. So I have to take the complex conjugate of psi1, so that is psi1 star, but it's in the left slot, so I have to star it also. Okay, and then I had, so that's my guy here, and then I simply have psi2 in the right slot, so I have simply psi2. And you see that this term is exactly the complex conjugate of that term. So they're not the same. Bummer. Because with this scalar product, this thing is not self-adjoint, and we have to solve a new differential equation. Okay, no good. However, these two terms are not completely different from each other. They're just complex conjugates of each other. So if you now do a trick, well, if you define a new scalar product, and let me just do that sort of with a different color so we don't have to rewrite anything. If I call it R, and I take the real part here, I take the real part of this whole thing, and you can check that it still satisfies the condition for scalar product. And so then if I take this guy here, this new scalar product, again, I have to now take the real part of that. Oh gosh, let me just make golden brackets for real parts so we don't have to write everything again. It's no fun. And the point is simply that we have to take the real part of this, and we have to take the real part of this. But these two guys are complex conjugates of each other. Well, they're only different in the imaginary part, but not in the real part. So that means these guys, once you take the real parts, these guys are equal. This is equal to the other. And we have actually a self-adjoint scalar product. That is good because that makes life so much easier. And so now we have, using this scalar product, we have now the left eigenvector of the linear operator, which is simply dA naught by d phi. And we now take our expansion, this equation here, and we project it onto that left eigenvector. Or if you want, that's a fancy word of saying multiply with the left eigenvector from the left, right? And use that scalar product. And so then we know if we do that, again, because it's a lot of writing, maybe allow me to do that again with just gold, so to speak, on top of it. So we multiply this with dA naught by d phi, and we have to take the integral over the whole period, and we have to take the real part, and this is in the left slot, so we have here actually a star, and that will be 0. And so we have to do the same thing on the right hand side. So that we need to write anew, because we need to work on that still a little bit. But let's just see, what do we need to do? We need to take the integral. We need to multiply this whole thing with dA naught star by d phi and take the real part. Okay, so what do we get? Now we have to be careful again so we don't make mistakes. So we take the real part of the integral from 0 to 2 pi of multiplying from the left with dA naught star by d phi, our right hand side, and that right hand side was d capital phi by dt times dA naught by d phi. I'll just copy it. I mean, we just saw what it is, and there's no point in scrolling up and down. We're just seeing these again. This is the same thing. dA naught by d phi plus 2q d capital phi by dx squared times d by dq of dA naught by d phi. This object integrated over phi is equal to 0. This is, what do we do with that? We want to have a condition for d phi by dt. We want to have an equation d phi by dt equals something. So you notice, if you ignore for a moment this kind of term, let's just focus on this very first term. This is simply minus d phi by dt times the absolute value squared of dA by d phi. Well, so if you integrate the absolute value squared times this object, and that's supposed to be 0, then this object better be 0 because the absolute value squared is positive definite. And so the point is that happens also here, right? This is also the absolute value squared. It's just here we don't see it yet because there's this derivative with respect to q. It's not so obvious yet. But we do see there's a dA naught by d phi. So this is, we're almost there. So we just need to figure out what this is. And you can interchange, of course, the derivatives here. So let's first simply calculate what is d by dq of A naught. So we have dA naught by dq. What is that? Well, that's d by dq of A naught is mu minus q squared e to the I phi. And if I take that derivative, I get 1 over the square root of mu minus q squared times minus q, right? Times e to the I phi. Well, fine. But what we want is we want to have dA naught by d phi. And so the d phi is here already. So that means we want to write this in terms of A naught itself. And that's not that hard because that's A naught. And we can simply, this exponential is A naught divided by this object. So in short, this is minus q over mu minus q squared A naught. And so now you can plug that into here, and you're done. Well, let me not write too much. So we're done, as in we can write this. This is also now a dA naught by d phi, and the d by dq makes this factor. And so we can pull out a dA naught by d phi from the whole integral, and we're left with a bunch of stuff with a phase. And so I'm going to write this down. So we have, this is dA naught by d phi, absolute value squared, integrated from 0 to 2 pi, times minus d capital phi by dt, plus d capital phi by dx squared, plus, well, not really plus, minus 2q squared over mu minus q squared times d2 phi by dx squared, the end integral equals 0. And so, as I said before, because this is positive definite, this actually has to be 0. So we can write this out. We get d phi by dt equals, and now you see this is, both terms are second derivative of the phase with respect to the respect to x, and what we have in front is a mu minus q squared in the denominator and a mu minus 3q squared in the numerator, and we have a diffusion equation. Write this as d of q, and you have a nice diffusion equation which is nonlinear, right? So one statement we can make right away, and we'll think about it more in the next session. We'll think about it more in detail. But one thing we can say instantly, that we can we get diffusive dynamics, and if d of q is positive, we will have relaxation, meaning just the wave number, the gradient in the wave number will relax to 0, and so we get a periodic solution. Whereas if d of q was negative, we would get that something is unstable and the gradients would not disappear, would not decay away. And so we have to look at whether the diffusion coefficient is positive or negative, and then we look at what happens when it is negative. But that's next time.